Can you hear me now?
Yes.
Okay. So yeah, hello everyone, and thanks for having me here and giving me the opportunity to present our recent work on multi-decadal variability in the tropical stratosphere. So as requested, and for those that don't know me, so I finished my PhD in 2018 at Lancaster University with Paul Yan and Oliver Wilde, where I focused on how climate and anthropogenic perturbations affect the stratospheric ozone and how those changes feedback on the climate system. So after finishing my PhD, I did a postdoc at CSIC in Madrid with Alfonso Saiz Lopez for 2 years, and that was with a focus on natural halogens and how they impact tropospheric ozone. So that was working with the so-called very short-lived halogenated species. And more than a year ago already, I joined Veronica's group at DLR, somehow dragged by Birgit Hasler. I think many of you know her. So here I have the chance to do something new that is developing machine learning-based parameterizations for climate models. Particularly, we are using a new initiative in Germany, which is the ICOS model, the non-icosahedral hydrostatic model. And that is developing radiation, convection, non-orographic gravity waves, and so forth with machine learning means. But also here in DLR, I have the chance to keep in contact with tropospheric and stratospheric ozone research, which I love. And today, I'd like to share with you a recent work that looks into multi-decadal variability in the tropical stratosphere. So I put here this plot to show you. So this is a cross-section, altitude, latitude. I just to show you the region we are most interested in this work, which is the tropical middle stratosphere. So if I can move on. So a bit of background, the transport of air masses in the stratosphere is controlled by the Pure-Dobson circulation, or the BDC. I'm not going to spend much time here, but just to mention that it is characterized by rising motion in the tropics, poleward flow in the stratosphere, and sinking motion at mid and high latitudes. More recently, it has been considered to consist at least in 2 branches, the lower or shallow branch, which controls the transport of air in the subtropical stratosphere all year around, and then the upper or deep branch, which is effective during the winter hemisphere. Because the Pure-Dobson circulation has been used to describe a broad range of stratospheric circulation, and there are different ways to describe it, such as the transform Eulerian mean, age of air, or the tropical upwelling mass fluxes. So in the introduction in this slide, I'm going to be talking loosely about the Pure-Dobson circulation and its changes, but later on, I'm going to define how we use or how do we diagnose the Pure-Dobson circulation and its changes in our work. So here we show a classic figure in Hardiman et al., where it shows a vertical profile trends in upwelling map fluxes, and it shows a very robust feature in climate models. That is that the Pure-Dobson circulation increased throughout of the stratosphere as climate changes in the century. But also you can see how models tend to converge in that the greater relative changes occur in the lower stratosphere compared to higher altitudes. And regardless, or in spite of this robust agreement in models of this acceleration in the Pure-Dobson circulation due to climate change, observationally derived changes in the Pure-Dobson circulation are more problematic. Somehow, reanalyses are more reliable, and yet substantial variability in the Pure-Dobson circulation over short time scale limits our ability to detect this long-term acceleration in the Pure-Dobson circulation in the middle and upper stratosphere. For example, this cross-section of Diallo et al. Using age of air show a an acceleration in the lower stratosphere in blue, but a non-significant deceleration in the middle and tropical stratosphere. So there has been some limitations in our knowledge detecting this acceleration in the middle and upper stratosphere, and that's part of our focus in this work. I'm aware that there are more recent papers in this year, particularly using EL5 and also SIM6 models. But here I'd like to show the literature that motivated ourselves this work when we started. So again, a bit more with the reduction circulation here. Marta, Avalos et al., using different reanalyses, also explore the reduction circulation, and they show that it has a substantial year-to-year variability coupled to different modes of natural variability. So particularly this time series of the tropical upwelling in the lower stratosphere from different reanalyses show a close relationship with El Niño Southern Oscillation, or ENSO, where you can see that El Niño event or a positive strong ENSO index is associated with an enhanced upwelling, and vice versa with La Niña events. Also, you can see how the QBO, or the quasi-biennial oscillation, is observed and is also related with changes in the reduction circulation, where the easterly phase is associated with a relatively quicker upwelling. Also, Marta showed this relationship by removing the associated signal with ENSO and the QBO via multiple regression means, which is quite evident for El Niño, La Niña event, and less so with the QBO, because the QBO, the signal peaks upper in the stratosphere around 20 hectopascal, and here we are looking the shallow branch at 70 hectopascal. But nevertheless, a key result that they have is that long-term trends in the reduction circulation, particularly in the upper branch, are unchanged whether removing or not removing the ENSO and QBO signal. So that made us think about what other modes of variability may be having an impact on the expected anthropogenically driven changes in the reduction circulation in the middle and upper stratosphere. So yeah, what other modes of variability? So the Pacific Ocean not only exhibit interannual variability related to ENSO, but also low frequency variability at decadal time scales that might be particularly noteworthy for the coupling with stratospheric variability, given that its impacts are felt globally. And it has been, for example, this figure shows that it has been associated with periods of strong warming during the positive phase of the IPO, and warming hiatuses in global mean surface temperature during the negative phase of the IPO. I talked too fast about the IPO. So the IPO, the interdecadal Pacific oscillation, or interdecadal Pacific in the Pacific Ocean sea surface temperature, is characterized by positive phase with relatively warm waters in the equatorial region of the Pacific, and a negative phase with cold water in the equatorial region. Also mentioned that we will be using this IPO index in our work, but it's been argued convincingly that it's not a single phenomenon, but rather a combination of various physical processes dominated by ENSO-like variability. Also, for those that are more familiar with the Pacific Decadal Oscillation, or PDO index, just mentioned that this is a similar but not equivalent proxy, because it is more influenced by the Aleutian law. But nevertheless, there is a strong correlation between the two indexes, and in any case, in our work, we use the IPO index, but similar results may have been found using this other index. So ozone. So far, we have talked about long-term changes and natural variability in both Pacific Ocean sea surface temperature and stratospheric circulation via the blue red option circulation. But here we also explore the composition changes in the tropical middle stratosphere with a particular focus of ozone. That's why I'm presenting here. So a bit of background on that. Despite of the first signs of global stratospheric ozone recovery due to the Montreal Protocol and subsequent decrease in stratospheric halogenated ozone depleted substances or ODSs since the year 2000 or so, even that detecting and attributing ozone recovery is still tricky. And this is because of the variability in other factors affecting ozone, such as dynamics, transport, aerosol loading from volcanic eruptions, solar variability, and all this complicates the detection of the rather small signal of ozone recovery from ozone depleted substances. So these two figures, a cross-section from Ball et al. And a time series from Chipperfield et al. Show that since around year 2000 or 1998, ozone in the upper stratosphere is rising again. And that may be likely the contribution of both, right? Decreasing halogens abundances in the stratosphere, but also the cooling as well due to climate change. However, there is a large variability in the extrapolar lower stratosphere that complicates the picture in that region. But nevertheless, we are interested in the tropical middle stratosphere, this region, and observations has been shown that ozone there has been decreasing since the 90s and remained relatively low since year 2000 or so. And in this region, even though ozone depleted substance, halogenated ozone depleted substances affect ozone, stratospheric ozone globally, in this region, ozone loss rates are most sensitive to nitrogen catalyzed chemistry, with its efficiency being controlled by its source gas emission, nitrous oxide, N2O, as well as changes in transport, and less so by those halogenated ozone depleting substances, as we will see later. So before we go into the results, in this work, we explore the connection between the Pacific Ocean low frequency variability, the strength of the advective blue red option circulation, and the knock-on impact in ozone levels. So we do that by exploring the multi-decadal variability in the blue red option circulation to better understand its long-term changes during the recent past, as well as relate how that low frequency variability in the blue red option circulation affect ozone level via modulating nitrogen chemical processing. So to do that, we use the community air system model, CSM, with the whole atmosphere community climate model, WACOM, that includes interactive chemistry in the stratosphere and the troposphere coupled to the radiation scheme. The model extends from the surface up to the lower thermosphere of around 140 kilometers, and it has a horizontal resolution of 2 by 2.5 degrees latitude longitude. Also, the atmosphere component is coupled to the land model, which calculates the removal of atmospheric tracer by dry deposition. So first, we have a simulation where we use to explore unforced or internal variability in the stratosphere. That is a simulation that is forced with a non-evolving pre-industrial forcings, where the model calculates its own sea surface temperature and dynamics in the atmosphere year after year. So it allows us to isolate this natural variability. Also, to explore the role of different forcings in the recent past, we use a run driven by observed forcing, both anthropogenic greenhouse gases and other pollutants, but also external natural forcings, such as solar radiation, volcanoes, and so on. And also this simulation is forced with observed sea surface temperature and sea ice. So we have two main simulations. one that includes internal generative variability only, and another that represent the real world, if you like. Regarding observations, we use the stratospheric water ozone satellite homogenized SWOSH dataset, which merges data from different satellites, accounting for inter-satellite biases, and provides, as you can see, a gap-free zonal mean from the upper troposphere to the upper stratosphere. Regarding SSTs, we use SSTs from NOAA, the extended reconstructed SST dataset. As I mentioned before, we use the IPO index, which can be derived using different ways, but in our case, we use the triple index from describing Henley et al., which is quite simple. It's just the residual of the deseasonalized area-weighted sea surface temperature from region 2 after subtracting region 1 and 3. And after that, I don't want to forget, we apply a low-pass filter, a Chebyshev 13-year low-pass filter, which is it captures the local maximum in the variance in the Pacific. So too quick. So first, we use the pre-industrial simulation to explore low-frequency variability in stratospheric ozone linked to the Pacific Ocean sea surface temperature. And this figure shows, as you saw before, the zonal mean cross-section ozone in altitude, latitude, regressed onto the IPO index. And that reveals a signal that peaks in the middle tropical stratosphere. And recall that in that region, you have seen that observations show decreases in ozone levels since the 90s and relatively low levels in the beginning of the 21st century. Then we also explore this IPO ozone fingerprint in the simulated recent past, including all varying anthropogenic and natural forcings. And you can see that the fingerprint is in agreement with observations, though there are some differences in the magnitude of the signal. But nevertheless, you can see that these simulations capture the fingerprint of the IPO in stratospheric ozone. And then just to mention that I mentioned before, but just to make it clear, while long-lived halogenated ozone-depleted substances have depleted stratospheric ozone globally, and changes in temperature can also modulate ozone loss, in this region, nitrogen catalyzed chemistry is the most important driver here. And it's affected not only by changes in the abundance of the source gas at the surface, but also by changes in transport, in dynamics. So let's try and break down this mechanism that involves dynamical and chemical processes linking the IPO with ozone in the tropical middle stratosphere. So now, to explore these dynamical chemical processes of the mechanism that we suggest driving this troposphere-stratosphere coupling, this figure shows the low-pass filter annual mean time series of the standardized anomaly of the IPO index, and also the various fields describing the mechanism in the tropical middle stratosphere, both for the 200 years of internally generated variability and 50 years of the recent past. The brood ozone circulation. So mentioned here that we diagnose the brood ozone circulation throughout this work using the advective vertical velocity of the transformed yearly area mean, that is neglecting isentropic mixing, but in the tropics they are small. So we can see that that the IPO index in red lines is highly correlated with relative changes in the brood ozone circulation in orange in both simulation throughout of the realizations. In turn, this variability in the brood ozone circulation affects the atmospheric composition, shown by its strong correlation with ozone, shown in blue, via the nitrogen chemistry owing to differences in transport time scale affecting the photo-oxidation of nitrous oxide. So overall, this simulation supports a mechanism that couples dynamics, the Breuer-Dobson circulation, and chemistry, the nitrogen processing, to explain this IPO Breuer-Dobson circulation ozone link, which is in agreement with our current understanding. And very briefly, so a positive phase of the IPO, remember those anomalous warm tropical sea-surface temperature waters, is associated with a relatively quick circulation that enhances the transport of N2O and therefore reduces the breakdown into more reactive species, which results in relatively high ozone levels. And the opposite is true for the negative phase of the IPO. This is aside from our work, so that this is not included in the paper, but I think it's interesting, and I'd like to share it with you. So back in the time when we started exploring this IPO Breuer-Dobson circulation ozone link, we wondered whether the signal was robust in other climate models. So to do that, we used two other models that included interactive ozone chemistry from the CIMIC-5 ensemble. And we also, instead of the Breuer-Dobson circulation diagnosed via the TEM, we use temperature because we couldn't calculate that. So the temperature here is a proxy for changes in the Breuer-Dobson circulation. And you can see that although the signal is somewhat weaker, is significant at the 95% confident level. And after that, we thought that exploring this mechanism in different climate models would be a very interesting follow-up work, but decided to focus here in the implications for the circulation and ozone during the recent past within the Wacom modeling framework. And that was motivated by the fact that that was the model that we were using, and we could run sensitivity simulations that would support our findings. But in any case, we could gain more insight by exploring this multi-decadal link in different climate models. For example, exploring what factors are important to capture this coupling, as well as other implications for the circulation and composition. But if I have time and you allow me, I will come back to this later on at the end of the presentation with a slide with an outlook. So to recap a bit, we have seen that the model simulations are the observations that we use, and also we have explored the mechanism that couples this IPO Breuer-Dobson circulation ozone link via nitrogen chemistry. Now, I will present in the second section of the talk how our results are important for the Breuer-Dobson circulation variability and its structural changes during the recent past. So, as I mentioned here, we explored this potential role of the IPO in modulating these recent trends in the Breuer-Dobson circulation. So this figure shows the time series, the trends in the annual mean Breuer-Dobson circulation for the base simulation over 1979 to 2010. That is the simulation that represents the real world, if you like. So we focus on this period because it allows us to explore or it contains the shift in the IPO from a positive to a negative phase, but also this period is more coincident with most observational and reanalysis based studies at the moment. So that's why we focus on this period. And again, we focus on both the shallow and deep branches, and you can see that in agreement with previous studies, the simulation shows an acceleration, a significant acceleration in the shallow branch, but a non-significant change for the deep branch, which is the main region of interest in this work. Now, by accounting for the IPO-like variability in the Breuer-Dobson circulation, that is removing linearly the congruent signal of the IPO from the advective Breuer-Dobson circulation, we show the long-term residual signal that may be closely linked to this increase in greenhouse gases and ozone depletion over the last decades. So now we show this other trend, and you can see how both for both branches the trend is steeper and statistically significant, particularly relevant for the deep branch, and this is between 10 and 7% per decade during this period. Also, because different observational and reanalysis studies that focus on slightly different periods using observations and data available at the time gave some inconclusive results for the deep branch. We also wanted to explore the sensitivity of these structural changes regarding the different time periods and endpoints. So to make that clear, for that, we calculated the trends for successive 20-year periods. That is, let's say, from first period is 1979 to 1998. The second trend is 1980 to 1999, and so on. And that is in order to better gauge the uncertainty of the long-term changes in both branches. And you can see here in the box plot that we show these 20-year running trend composites that includes 12 individual trends. And again, it shows that for the shallow branch, the Breuer-Dobson circulation is significant regardless the period, but for the deep branch, the trend is negative, but it's insignificant. And it's after we remove the IPO signal that this trend in the deep branch of the Breuer-Dobson circulation is positive and significant regardless the chosen periods. So we believe that our analysis to a first order of approximation demonstrates that accounting for unforced climate variability can help reconcile our theoretical understanding of this acceleration in the Breuer-Dobson circulation in response to greenhouse gases with previous estimates using reanalysis and observation over the recent past in the deep branch. Yeah, so a valid question that could make ourselves is how important could this be or relevant in longer time series or periods of interest? And that could depend, right? For example, what would happen if we would have used the full time series from 1960 to 2010? And that's what we are exploring here. Again, this is not shown in the paper, but I think it's interesting, and I would like to share with you. So we would have found that the long-term trend in the Breuer-Dobson circulation for both branches were very similar. A bit accentuated in the shallow branch, but negligible changes for the deep branch. So note that the Breuer-Dobson circulation, the IPO is an index or proxy for multi-decadal variability in the climate system, and therefore it fluctuates from one mode to another. So in this specific case, coincidentally, the periods start in a negative phase of the IPO, then switch to a positive phase of the IPO by around 1980, and then switch back to a negative phase of the IPO by around year 2000. So one may think that the longer time periods in the future, the greater greenhouse gas induced climate change signal in the Breuer-Dobson circulation acceleration, right? That could rise from natural variability. But also we can see here how small often are those perturbations, particularly in the deep branch of the Breuer-Dobson circulation, compared or against the background natural variability. So, but nevertheless, I wanted to show this because I think this is a very graphical and clear example of how important is accounting for different modes of natural variability at different time scales, depending on our problem, our research question, when exploring those anthropogenic perturbations in the climate system. This is also interesting, and this is not included in the paper, but I think it's interesting. We learned something here, and I like to share with you as well. So recently, it's been shown that the cooling in the stratosphere, that is, this cooling in the stratosphere, it's how it shrinks due to climate change, has not been taken into account in previous studies that looked into changes in the broad absorption circulation over the 21st century. Because those studies usually use the transform area mean or the advective broad absorption circulation with a constant scale height. And this, they argue, Eichinger and Sasha Roland, they argue that because of that, they may have been overestimated the acceleration of the broad absorption circulation by around 20% by the end of the century. So here we were interested in understanding whether our results were sensitive to the details of how the advective broad absorption circulation is calculated. So this is the plot that you saw before, and this is the changes of the broad absorption circulation as the same before, but using their method, that is taking into account the cooling in the stratosphere for those changes in the broad absorption circulation. And you can see that we found negligible differences. We think that the fact that we found negligible difference with the two methods, the two approaches, and that they found a large difference in trends in the broad absorption circulation, it's related to the fact that we are only exploring 32 years in the recent past, and they are exploring 140 years, where the cooling by the end of the century, particularly for the RCP 8.5, it's way greater than in our simulations. So yeah, this is not included in the paper. I think it's important. I would like to share with you that bit. So and third, so having explored the mechanism that couples this IPO broad absorption circulation ozone link, the importance of the IPO-like variability in the broad absorption circulation, in the third section, we now consider the role in recent ozone trends, which might be more relevant for your group here. So first, we evaluated ozone in the tropical middle stratosphere for our base simulations, the recent past simulation with the SWOSH database. Also mentioned that the simulation of this setup is more detailed. The evaluation is way more detailed in Tilmes et al. Simon made a really comprehensive evaluation if you are interested in, but nevertheless, you can see that our base simulation is in good agreement with the SWOSH database for both the annual mean in absolute levels, but also in variability, as well as for the 10-year running mean ozone trend for the periods of interest that capture this shift in the IPO phase around year 2000. So that was the evaluation, and now here we explore those changes in mid-stratospheric tropical ozone. So the upper panel shows this 10-year running mean time series of ozone in the tropical middle stratosphere, as simulated in blue and observed in black. And the lower panel shows the low pass filter index of the observed sea surface temperature. And you can see how those negative ozone trends in the 90s and the low levels since year 2000 are consistent with the proposed mechanism. That is that a relatively cold tropical sea surface temperature in the Pacific are related or associated with a relatively weaker circulation that in turn enhances the breakdown of nitrous oxide and therefore enhances ozone loss. So that is consistent with what we are proposing, but there are many other potential drivers that could be playing a role in these recent ozone loss trends. And for that, we used or ran a series of sensitivity simulation to explore the role of anthropogenic halogenated ozone-depleted substances, as well as changes in nitrous oxide emissions, also volcanic eruptions, and the effect of variability in sea surface temperature. And here we show the results, and by assuming that the different drivers affect ozone linearly, you can see that emissions and levels of halogenated ozone-depleted substances and nitrous oxide together account for up to a fifth of the simulated trend. Major volcanic eruptions account for another quarter of the trend, but is natural variability in sea surface temperature that accounts for half of the recent trend. If we see the realization where we fix anthropogenic ozone-depleted substances, you can see now that ozone anomalies clearly follow the IPO variability, explaining very little of those recent ozone loss trends. But now, if we looked into in red, if we looked the realization while we fixed sea surface temperature, it shows the overall ozone depletion in the last decades associated with ozone depleted substances, but it does not fully capture variability as in the base simulation, particularly if you see where the IPO changes phases. And this is what explains half of the recent trends in ozone in the tropical middle stratosphere. So we think that these results show that recent negative trends in ozone in this region are not primarily driven by anthropogenic perturbations, but rather due to natural variability. So getting closer to finishing, to summarize the three takeaway messages of this work, we have seen that although climate models show a robust long-term acceleration of the broad absorption circulation due to greenhouse gas-induced climate change, the observational evidence has been somehow more limited, particularly in the middle and upper stratosphere, due to this large natural variability and relatively short periods. Also, and in spite of the first signs of global ozone recovery, tropical mid-stratospheric ozone has declined since in the 90s and remained relatively low since. So here in this work, we demonstrate that multi-decadal variability in the broad absorption circulation coupled to the Pacific Ocean can help us understand its structural changes in relatively short periods. So accounting for the IPO-like variability, the resulting broad absorption circulation trends is significant and steeper in both branches over the 1979 to 2010 period, suggesting that natural variability masks a large fraction of this long-term acceleration, particularly in the upper stratosphere. Also, via a series of sensitivity simulations, we showed that sea surface temperature can explain up to 50% of the simulated ozone decadal variability through dynamical and chemical processes. And as a whole, I think that this work shows how internal climate variability on multi-decadal time scale can influence transport and composition in the stratosphere, highlighting the needs for a good representation of natural variability in climate models if they were to be used to distinguish between forced and unforced signals, for example, such as a future ozone recovery. So this is just to acknowledge the team behind this work. I'm not going to spend time here, but you may see some names that you are familiar with. And now at this part, I don't know whether I have time. Gabriel, do you think I have time to go through some answers?
I think we should probably come to the end. Yeah.
Okay, then I can leave it here, and if I have questions, then I can go through the outlook.
Okay, thank you very much, Fernando, for this very interesting talk. First of all, I would like to